Civil and Environmental Engineering Department. I'm working with Dr. Daniel Dowden in structures, especially structural dynamics. I put together this shake table this summer for a summer youth program sort of thing. So, but before I show this shake table, I want to show you the video of a real shake table. My professor, my advisor, during his PhD, did some real, well, not full scale, but small scale shake table experiments on a frame that he was designing. So, just press play on that. There we go. So this is the University of Buffalo in Washington, and that's a frame that you put in a building to resist earthquake or other lateral loads like wind, and it's meant to dissipate energy like damping in the form of the steel plates that are in the center. So this is just one example.
So how big is the system? Do you know?
I think it was third scale, so maybe that would be like 20 feet tall, something like that. So
that's 20 feet tall. That's
yes,
huge.
yes. They have very large shake tables at the University of Buffalo. It's state of the art. So this is a smaller version of it.
Let me explain a little bit what's happening here.
Sure.
So this bottom one you see is the shake table. That's vibrating in the horizontal plane. Okay, and this is a building that's responding, right? And when we do research, what we do is we try to change the stiffness of the system by changing the poles and what type of material we use, how do we change mass, columns, and so on. And then as the stiffness changes, the natural frequency changes, right? And there are accelerometers, there are sensors over here, accelerometers
Yes.
measuring the response of the system to an input. So there are different types of input that we can put in that system. We can put a harmonic input and measure the harmonic output at a given frequency. Now we can sweep these frequencies and see harmonically at different frequencies how does the structure respond. Or the other test that you are seeing over here is more like an environmental load. So it's a combination of summation of different frequency signals. You put that together and you excite the shake table and you see how the system responds.
Yes.
Okay.
So this could be idealized to a multi-degree of freedom system where you have, and you could simplify it to essentially 3 nodes. So you have 4 nodes. 1 at the base, and then first level, second level, third level. And each of these plates right here, as you can see, is kind of large. It's a big chunk of mass, essentially. So you have masses, and then stiffness comes from the plates as well as the columns, and then the damping comes from just the energy dissipation that's inherent in the system from the yielding of steel and such. So here is just a Knex shake table that I made, and on here is it's supposed to be like a moment frame building. A moment frame building is essentially where you just have rigid moment connections at your beams and columns, so you don't have any lateral bracing going diagonally. So these parts right here are the moment frame connection, and the rest of it's pretty much just pinned. There's masses on each floor to add mass in the system. With no mass in the system, if you have an acceleration, excitation, there will be very little effect seen by the structure. The mass is what causes the force. The more mass you have, the more force you have. So I'll just get it going and show some force vibration and see how it resonates.
Can you even see it? If you want, you can come
See
closer
it?
to it.
So when I get it to higher frequencies, it doesn't resonate with structure. But when I get it down near its resonant frequency, that's when you're going to see the majority of the displacement and force on the structure. If you can see it, you might be able to see that these pieces are sliding back and forth on this rod right here, and that's causing some friction dissipation, which causes the damping in the system. If there wasn't any damping in the system, I'd be able to get it to resonate even more. If I get it to a little bit higher frequency, I might be able to get the top to stay still. You see there's different modes of vibration. The first mode is going to be where the top is moving back and forth the most. Second mode is essentially where you have this. And then third and higher modes are going to be different sorts of shapes. So this is a moment frame building where it dissipates energy. I have,
Let me
yeah.
So in this, how many degrees of freedom are we actually, let's say if you have a model as simplified model. What? 6. How? You want to explain the 6 degrees of freedom number? Anyone? Come on.
I'd say 4.
How many?
4.
4. What are those?
There's the direction that each mass can move
Each
relative to
floor.
the
So 1, 2, 3, and 4, right? So why is this not a degree of freedom? Yeah, but is it not moving?
It's a reference.
Reference. Oh, we didn't bring that up when we talked about degrees of freedom, right? The answer is, our definition of degrees of freedom was how many independent variables do we need to decide how many degrees of freedom some system has, right? So this one, we can consider this also as a degree of freedom, and we say 1, 2, 3, 4, 5, but we are constraining that degree of freedom by the displacement or force that we are giving it. Okay, so in resultant, we are not controlling directly 4 degrees of freedom or constraining directly 4 degrees of freedom. System.
Yes.
Okay.
This is the forced.
This is the force degrees. Okay.
Yeah.
So, but yeah. So that's the reason when we write, we have 5 nodes with 4 degrees of freedom system. And the other thing is, you guys are not even considering degrees of freedom swaying this way or twisting. So in that case, each node point can have 3 degrees of freedom, at least for this. So we can complicate it by having each node 1 degree of freedom, or we can model it by 3 degree and 12 degrees of freedom. Huh? 12, we can model it as 12, or we can model it as 3, or we can also model it as just 6.
So what are if you model it as 12, what are the 3 degrees of freedom at each floor?
Oh,
This can work the same.
this one. So at each floor, one is moving in this direction.
Okay.
Let's say that's X.
Okay.
One is moving in Y direction.
But is it really?
See, this is moving.
Okay.
Yeah, okay.
Okay. The other is each degree rotation.
Okay.
It's twisting. So each point can rotate, can move along X, can move along Y.
This way.
Especially for buildings, we cannot move it up and down. That's an assumption. That's a good assumption.
Yeah.
Okay. Having said that, all my research is trying to find the vibrations in Z direction. So in that case, we cannot assume Z is 0. Yes, that's a good point.
There is vertical vibration in earthquakes. We do have records of that, but it's not as significant as the lateral forces. Generally speaking, you design buildings to resist vertical loads. So
they should be.
They should be fine if you have a little bit of vertical vibration. So.
Okay, that's not the damage. That's not how the building would fail. Let's put it that way. So the building might fail in other approaches. So that's what makes it important for us to model and think about those. Okay, now I'm going to talk about this.
Here's this different building. This is, as you can see, it's braced. So it has these X braces in here. I designed these braces so that they're tension only, which is very common within buildings. So if you have just a long brace that's supporting something, if you apply compression load to it and you don't have any bracing on that brace, it'll buckle. So usually when you're doing bracing like this in a structure, you assume that it has no tension or no compression capacity. However, braces also yield. So braces elongate if they get the yield zone. And yielding is the way that buildings dissipate energy during earthquakes. So there's a phenomenon with braced buildings like this called period lengthening. It's essentially the building getting damaged. So I'm going to try to show that. We'll see if I can get it to happen. So first of all, I need to get it to its resonant frequency, which is going to be pretty high. The building's a little more wiggly now. It's taking some damage. So I'm going to try getting a little lower frequency. It is a little bit softer. I'm going to force it to be a lot softer. Oops, without breaking it. Just to speed up this demonstration a little bit. So now I have it even more damaged. So this is if it went through some more sustained damage. So now it's excited at a much lower frequency. So this is a demonstration that your stiffness of your building is going to be the stiffness of your building is going to be directly proportional to your frequency. Yeah, and it also shows the importance of if you're designing a building, you want to keep in mind that if it's damaged, it can lower the frequency at which it's excited. So that's something that we have to look at in my research group.
So there is a whole research group called structural health monitoring or condition monitoring. Have you heard of that? Okay, so just like humans have health, structures also have health. Okay, we are trying to monitor the condition or the health of a structure, especially a building. So in this case, the idea is as buildings grow old, they don't have the same stiffness. Okay, they rust or they just decay over time, and the stiffness reduces. What happens when the stiffness reduces?
Your frequencies are going to change, right?
Change how?
Decrease.
They decrease, right? So in structural health monitoring, one of the main things is we try to find the natural frequencies of the system and mode shapes of the system and track them over time. So there's actually a paper in IMAC, it's on IMAC conference, and this researcher has been studying a building for like 20 years. Same building. And and it's a very thriving research. Right now where it is at, if someone is interested in research, is it's easy. There are three things to say. One is there a damage? Second thing, where is the damage? Okay. The third thing is how long can I still use the damage? How much more life does it have? Okay. So for example, if you have your tire in your car running, is there a crack? Can you know it beforehand? Because crack doesn't develop just like that, right? Unless someone poked. So there's crack development over time. can you know it as soon as there is a small micro crack? And can you keep progress of it? Can you know where it is? And the next thing is, can you say, how long can I use it before I have to replace it? So the prognosis part is where the active research is happening.
Because if you don't keep an eye on it, it could be like this. Nobody wants to be in that building. I just have a couple more slides. Just,
So, if a building is damaged, will its natural frequency always become lower?
Yes, unless there'd have to be something weird.
So,
Generally damaged means your stiffness is decreased. The only thing I could think of is if you had a part that was meant to move that got seized up. So if there was like a joint that was supposed to rotate and then got rusted out and kind of got locked up, which that's common in, for example, if you drive along highways and you see those bridges where they kind of have like a pin and hanger thing on some of the beams. If you've ever seen those, it's like on an overpass, the beams kind of hang in there off this pin. Those are known to seize up, and that causes stiffness problems where the stiffness increases in the system. But generally speaking, if something is damaged, the stiffness will decrease.
and damage can also mean that one whole floor is removed, right? Someone just took off parts of bricks and threw it away, so mass is reducing. So that means natural frequency can increase.
Yes.
So it depends on a lot of things.
So just a brief thing about the shake table. Again, we developed it as just a low budget earthquake engineering educational tool, since like shake tables that you can buy are generally going to be thousands of dollars. So, and we're using it to demonstrate relationships between frequency, mass, and stiffness, like I showed, and the behavior of different lateral frames. So, and I also have some systems, so like you can show base isolation, rocking frames, like non-conventional systems. Just a brief word about our research group. My advisor is Dr. Daniel Dowden, as I said before. Another colleague of mine is Armin Tatar. He's Dr. Dowden's PhD student. We work to designing structural systems that are resilient to earthquake events, so they can take a dynamic load and still be usable afterwards. So we're working on cross-laminated timber buildings, which is basically panels of wood put together to make a building, as well as buckling restraining brace systems. So it's like these braces, but they don't buckle. So, yeah.
That's good.
Yeah, that's about it.
Thanks, Alex.
Any other questions?
Did you, so you helped design this shake table? Or
This was all me.
You did
Design. Yeah.
Did you publish the design somewhere for like other?
No, we're working on it.
Okay.
We're working on having a publication out for it. So.
Okay. I think mine truckers would be interested in exploring
Yeah.
that.
Yeah, we had a STEM group come to my previous lab, and we did the top part, not the whole part. And we had a shake table, and we shook it till it broke.
Yes.
So we had 5 or 6 teams of girls, designing high school girls. The STEM program, they came in, and they loved the buildings crashed up. You know, it's fun.
I can get these things to break. I purposely made it so they won't break.
No, that's good.
Demonstration.
Yeah, but it's
yeah.
fun.
I could add more mass to increase the force in the system. I could have more floors to increase the second order effects, the P delta effects.
So where do you think is the maximum displacement in this system? The high floors or the low floors?
You're talking about relative between floors, inner story,
No. Overall cumulative displacement.
Well, if we're looking at his first model, it seems like if you're looking at the low frequency, the high floors are the ones that seem to be displacing the most.
Mm-hmm. Generally, it's always the fundamental which has maximum displacement.
yes.
For the first frequency. So the top floor. So after looking at this, does anyone want to be on the topmost floor in a high-rise building? You know, the view is great, the wind is great, and everything is great, but you have vibration
I
problems.
feel seasick all the time.
Did you say it's the first natural frequency that makes the most displacement?
Okay, yes. When we drive at the first natural frequency, we tend to have the maximum displacement. Okay. I think I see a question coming there. Yes.
A little bit different, but, so we know that structures will decay over time. Do specific elements also decay over time? And if so, do we know like the properties of like what elements like decay at what rate over time?
I can answer that a little bit. So referring to decaying over time, if you have like a steel beam or something, the decaying over time would really happen either from deterioration of such as rust, but if you're in a building and has rust protection and stuff, that's probably not going to be as much of an issue. What I showed with that building was if you have excitation of the structure and you yield the members. So in steel, it's usually yielding that's going to cause that. And then with concrete, actually, sometimes you can have the opposite. Over time, concrete actually increases in stiffness to a certain point before it deteriorates because it's a chemical.
It cures.
It cures and it increases strength over time. So, so there's that. So I guess it really depends element to element, and usually you're going to get most of your damage accumulate during like seismic or wind events. But generally, seismic is when you usually design everything to be elastic because it's windy a lot.
Yeah, buildings have a very high safety factor.
So that way element type selection doesn't almost play that much of a role as
So
much
it
as
takes
structure. Of course.
long time for it to catch up and damage for us to actually notice.
And you were saying concrete increases. How does that work again? You mentioned a word, but I didn't
So,
recognize that word.
have you ever worked with superglue?
Yeah, a little bit, yeah.
Okay, what happens? Initially, is it stiff? It's sticky, right?
Yeah,
Okay, but if you leave it over time, its strength increases?
yeah, it solidifies and stuff.
Yeah, that's what is called curing.
Okay,
That's what is curing. Concrete also has similar thing, but it takes much longer time for it to cure.
okay, so even after like the
Right.
initial set.
Years, months and years.
I believe the concrete in the Hoover Dam is still curing.
Okay.
So in the center of it.
Does it increase stiffness?
As it cures,
I believe so, yes, it does. Because the concrete's elastic modulus is proportional to the square root of its compressive strength.
So do you have to take that into consideration with the buildings, like you said, the damage would decrease the natural frequency over time with the natural frequency increase?
so you're talking about decades of change in natural frequency. The first immediate change is, let's say there's a building just opened. So just before the opening, the building is empty. Okay, just after opening, people come and move in stuff and things. There's an immediate increase in mass of the building. That's where your sudden natural frequencies change. So every day when you guys leave this building, your natural frequency drops. Okay, and when you come back, natural frequency increases.
Yeah.
When you come back, natural frequency decreases because you're adding mass to the system, so natural frequency reduces. Okay, and the same thing, whenever there is a snow, there's huge amount of mass at the top of the building, that changes how the natural frequency is. So temperature affects the stiffness, right? If something is hot and warm, then its stiffness is low, right? Same thing happens to buildings and to bridges. So during daytime, when it's really sunny and hot, the stiffness is low, so the natural frequency comes down, right?
So do civil engineers up here consider building a structure differently because of like the -40 and stuff below that we had last year and stuff like that versus like someone in California?
Yeah.
Or is there not that much of a difference?
You're expecting a drastic change in natural frequency, which is not the case in buildings.
Generally speaking, we don't have to worry too much about vibrations in building in Houghton because it's not super windy and you don't have like hurricane effects to worry about and you don't have earthquakes here. So if you're actually designing for seismic effects for buildings in Houghton, if you look at the seismic map, the criteria for loading is you can neglect them entirely. So unless the Keweenaw Fault becomes active again, we don't have to worry about that. So most of the lateral resisting in the buildings around here are going to be for stability and for the wind that we have. There might be some vibration stuff, but there's simplified procedures, and I'm sure that because of our low loading, people use simplified procedures here that have been developed. So.
Okay. You have a question?
Stay out for flooding.
Flooding?
Yeah, that's adding mass and doing a lot of damage.
I mean, I don't know if there's vibration.
There is, especially when they design bridges, the poles and bridges, you have water coming in the columns and there's vibrations for that. Yes, there's a huge study on that. Okay, let's get back. Now that you've been